All right. Dr. Daniel Cohan is an associate professor of civil and environmental engineering at Rice University. He also serves as a faculty fellow in the Baker Institute, Center for Energy Studies, and as a member of EPA's Board of Scientific Counselors and the International Energy Agency's Electricity Security Advisory Board. Dr. Cohen received his bachelor's in applied mathematics from Harvard University and PhD in atmospheric science from Georgia Tech. He also served as a Fulbright scholar to Australia. He authored over 50 peer-reviewed publications, 75 op-eds, and a book titled Confronting Climate Gridlock: How Diplomacy, Technology, and Policy Can Unlock a Clean Energy Future. Today, Dr. Cohen will be talking to us about modeling the potential for geothermal electricity in the United States. Whenever you're ready, Dr. Cohen, please begin.
Okay. Thank you, Noor. Great to be with you virtually. Do hope to come and visit the center sometime later this year. I got this invitation in December, and you had a couple of slots to fill very early on, and so was able to do this remotely. But I've started getting to know Ken Wizian through a council that we serve on, and I'm very interested in the work that goes on at the Bureau. So I'll put up the slides. Okay. Are the slides showing up okay?
Yes, we can see.
Great. Yeah, so the topic today is modeling that we're doing, electricity systems modeling, about what role could geothermal play in various grids across the United States. And acknowledge the people who've worked with me on this. Richard Morse, when he was an undergraduate in the group, he's now heading towards a PhD program, deciding where to go. Chen, who's a PhD student in my group, who did the bulk of this work, and then our colleagues with Project Interspace, who we've been interacting with, and they bring a lot of expertise from the oil and gas and geothermal industries. And the motivation for this is that we're going to be seeing a huge growth in electricity consumption. Electricity has been kind of a dormant industry in the US and Europe and many developed places recently. Of course, it's growing very fast in China and developing parts of the world. But after decades of growth, we've been through about 15 years where outside of Texas and most of the country, electricity demand has been pretty flat. Efficiency has kept pace with economic growth. But if we're serious about decarbonization, that's going to require a lot of electrification. That's going to require more electric cars, more electrified heat, more electrified industry. And so most projections are that we're going to start seeing an inflection point and start seeing a big uptake in electricity consumption, and probably need 1.5 to 2 times as much electricity as we generate now by 2050 if we're serious about decarbonization. And various studies have pegged that number at different places with some uncertainty. There's also growing expectation that renewables are going to be playing a bigger role in this. And here I show 4 different forecasts that have come from various groups, from the National Renewable Energy Lab on the left, from Bloomberg New Energy Finance, from the EIA here in the US, and then the International Energy Agency on the right. And you can see this trend that's happened over the course of the years, where the lighter beige color being where forecasts thought we would be in 2015, the gray line showing the most recent forecast, and then for 2 of these cases, we have a 2022 forecast, the black line, and you see this upward trend in terms of what percent of electricity generation is expected to come from renewables, even under a business as usual scenario, even if we're not heading towards a deep decarbonization case or fulfilling President Biden's goal of 100% clean electricity by 2035 or net zero economy by 2050. Even without that, just with the policies in place, just with technologies trending as expected, 8 years ago, it was expected, 9 years ago, it was expected that we would only have perhaps 1/3 of electricity from renewables. Now the forecasts are, in some cases, some forecasts showing more than half could come from renewables. But for the most part, those forecasts by renewables mean mostly wind and solar, mean mostly variable forms of electricity. And in projections like that, it's going to give a lot of challenges for grid operators, a lot of challenges in keeping the lights on all the time, a lot of huge fluctuations in what electricity supply is going to look like. And so the figure on the left shows from EIA what, on a national average basis, electricity generation looks like as of a recent year. And so you see the supply stack that meets demand. On average, of course, it's different days, different seasons, different part of the country, but on average, we use more electricity in the middle of the day than we do at night. And traditionally, and in recent years, that's been met by the sort of steady output from coal plants and nuclear plants on the bottom of the supply stack, and natural gas combined cycle being now the biggest source of electricity in much of the country, and green being wind, which of course, averaging it over 24-hour cycle over the course of the year doesn't reflect just how variable that is. And solar, of course, has the variability with the sun. By 2050, even in just a reference case, this is a case that doesn't have any new efforts to try to go to cleaner technologies. It doesn't at all meet President Biden's net zero target. It's just where they think we might be headed under base case conditions, base existing policies, is going to be this dramatically different looking curve. More demand overall, and this huge growth in solar. We've seen solar amounts doubling every couple of years nationally, doubling even faster sometimes in Texas. And so this big bulge where we're going to, in some cases, have more electricity than we need in the middle of the day, and have gaps that are going to need to be filled in by storage, by gas, by some other thing as the sun sets, and these big ramp downs that are going to be a challenge as the sun sets in many cases, and some scenarios that they've looked at in which it could be even more pronounced. So for example, on the right, again, this isn't even as ambitious as having any new policy. This is just saying with existing policy, if wind and solar become even cheaper than their baseline scenario, and historically, EIA has always underestimated how quickly wind and solar have gotten more affordable. If they continue on a fast improvement in technology, a quick lowering of costs, we could have this even more dramatic roller coaster of wind power gets generated. If, on the other hand, we are serious about going to net zero, if we really do take our pledges seriously, as we have pledged to the under the Paris Agreement at the COPs, the Conference of the Parties, we've pledged to be net zero economy-wide by 2050. That's going to require electricity to decarbonize first, because there are going to be parts of the economy, airplanes, overseas shipping, certain industries that need very high temperature heat that are going to be hard to decarbonize. And so we're going to need electricity, which has so many zero emitting options, to decarbonize first. And so when people have looked at net zero strategies, it's going to have even more of a reliance on renewables. Or there are scenarios where you could have more nuclear scenarios of other ways, but most groups, when they look at where the costs are, when they look at where the resource availability is, they think wind and solar are going to play a huge role. So this is an example from Princeton's net zero study. They show a reference case where even in the reference case, you see the light blue wind growing, you see the solar growing a bit, but in the reference case, natural gas would still be over half of the energy supply. But in their modeling, any scenario that gets us to net zero economy-wide by 2050 is going to need almost all of our electricity to come from zero carbon sources. They have different scenarios of how to get there. The E, whether it's a plus or minus, means do we have more electrification or not? Do we have more electric cars, more electric heat pumps and electrified industry, or do we go slow in that way? B means do we have a lot of biomass in the mix? And they have different scenarios where RE minus means we constrain renewables because people might be opposed to wind farms or solar farms. RE plus means we don't have those constraints. We build the transmission we need to enable renewables, and renewables continue to fall in cost. So you have scenarios like the one on the farthest right, where wind and solar become absolutely dominant. And because we have lots of electrification, we have a tripling of power demand. You have scenarios like this next to last one, where local opposition makes it hard to build more wind and solar farms. But even in those cases, we still build a lot of wind and solar. Perhaps in a case like that, we see a resurgence of nuclear power. But all of these have, if we're serious about net zero, we're going to have an enormous role for wind and solar. In those scenarios, if you looked at any of those, you might have noticed that geothermal really doesn't even, geothermal gets just this little sliver, this red sliver, if we've restricted other renewables. If wind and solar are hard to site or hard to get permitted, if land is a concern, then they have this little sliver provided by geothermal. And in the others, you really don't see that red sliver. So they have scenarios where we could get to net zero without needing geothermal at all. And it's absolutely true that there are plenty of pathways where perhaps we rely on nuclear, perhaps we have battery storage, perhaps we blend wind and solar in various ways. We can get to clean energy without geothermal, but there could be a role that it could make it more affordable, that it could make it better balanced. It could reduce the battery needs if we have a bigger role. On the left shows another example. This is a group by Williams and others. Williams is a professor at University of San Francisco who's done lots of decarbonization modeling studies over the years. Again, this nearly invisible sliver that geothermal might play. Studies by Mark Jacobson at Stanford, who leads the Solutions Project and has come up with various scenarios of what he considers to be optimal ways of getting to net zero. And in his case, he tries to get there without nuclear in ways that are quite controversial with some people who say that we should keep nuclear and carbon capture in the mix. But he, by sort of fiat, decides not to have those in the mix. But even leaving out nuclear and leaving out carbon capture in his solutions, he thinks that geothermal would be less than 1% of an optimal 100% renewable mix. But there are some other scenarios that could give a bigger role. So this is National Renewable Energy Lab, some ways that they looked at. They considered, what if we took President Biden's commitment seriously of wanting 100% clean electricity by 2035. Obviously, we're not on a track with that policies, but that's the ambition that President Biden set. So if we were serious about getting there, what you see on the right panel is NREL's scenarios of a variety of ways that we could get close to 100% clean electricity by 2035. And in all of them, wind in light blue, solar in yellow have a huge role. Storage in pink helps balance wind and solar. And in similar to Princeton, in one of their scenarios, they lumped it together. I don't remember exactly how much was biomass, how much was geothermal. But if, again, we're in a constrained case, which in some parts of the country we appear to be, there's growing amounts of local opposition, people not wanting wind farms in sight, people concerned about carpeting large amounts of land with solar. So if we start to see more and more of those constraints on wind and solar projects, then we might build this substantial chunk of either biomass burning or geothermal power plants, different ones depending on whether you're in a geothermally active or hot subsurface conditions for geothermal, or if you have more biomass waste. Different parts of the country would do different things. A problem with this constrained case, though, I will point out is, people who look at geothermal might want this, but this constrained case, by limiting how much we could do wind and solar, does have 2 cents per kilowatt hour higher overall electricity costs than the all options case. So it does come at a cost. It could hurt the ability to decarbonize cars, decarbonize heat pumps, and industry if we constrain and we limit the wind and solar in that way. We've done work in a couple of papers over the years, and this is work that Richard Morris did while he was an undergraduate in my group, we've specifically modeled the situation in ERCOT and tried to see how far could we push things with the growth of wind and solar here in ERCOT. And what we found is that most of the time, wind and solar are very complementary with each other. So they can be their own backup. They can limit the need for storage. They can limit the need for nuclear or geothermal or batteries and so forth by balancing each other, especially if you have wind from different parts of the state. If you don't just do West Texas wind like where it was first built, but you also have South Texas wind where you get the afternoon sea breezes kicking in just when we need it most on summer afternoons and evenings, blend it with solar, which generates at the times you would expect, it balances itself most of the time. What we found, though, is even with an optimal mix that we tried to make wind and solar as balanced as we could within ERCOT, if ERCOT continues to operate as an island, disconnected from most of the rest of the country, then what we found is that about 9% of hours over the course of the 3 years of meteorology that we considered, 9% of the time when neither is it windy nor is it sunny anywhere in Texas. And times, so where we measure that in terms of the overall combined capacity factor of an optimized portfolio of wind and solar with the wind distributed as well as we could around the state, still had a lot of these hours when you would only get a 10 to 20% capacity factor out of your system. To not be alarmist, in all the years we looked at, and these are historical, so you'll notice that the loads are lower than they are today. For example, ERCOT's projecting over 80 gigawatts of demand during the freeze we're going to get next week, which will be a wintertime record. But in general, when you get the lowest output from wind and solar combined, is not the hardest times for the grid to meet as long as you have other sources around. It tends to be on September evenings. It tends to be on spring evenings, times when the sun has set before the winds have picked up, whereas it's usually pretty sunny during the very hottest hours of the year. It's usually very windy during the very coldest hours of the year, at least that initial period when a cold front passes through. But we can see that there are times that are hard to meet. So this shows what the pattern looked like during what Weather Channel likes to call Winter Storm Elliott, which was the December event, that sort of Christmas Eve freeze that we got in 2022. Those looking at the data, I think the freeze we're getting next week is going to look a lot like Winter Storm Elliott. Fortunately, going to be about 10 degrees warmer than Uri was, the one that caused the blackout back in 2021. But we're likely to see a repeat of an event about like this, maybe a little bit shorter than that event was. And you see when it was absolutely coldest, wind does very well. You have the cold front coming through, bringing wind, but you were moving towards a time where the toughest period ends up being, at least in wintertime, when the winds have slowed down and it isn't sunny yet. And so this red period is actually what was hardest for the grid to meet. The browns show how much had to come from fossil fuels. The gas and coal had to run the hottest. The highest prices actually came not when demand peaked, but when net demand peaked, when net load peaked, when we didn't have much wind or solar around. And so we had to run our power plants highest at that red point. We had very cheap power, plenty of reserves at the green point that grids used to try to manage for. So how does geothermal come into the mix? Well, enhanced geothermal gives us a dispatchable option that we can have operate whenever it's needed. It could be a firm baseload option that tries to run as much as possible to get the most megawatt hours on the grid. Or there's been a growing amount of research, especially coming out of Jesse Jenkins' group at Princeton, looking at how geothermal plants might be operated in more flexible ways to give you that blending. Could you store up energy, heat underground? And could you release it when the grid needs it most, when we have this roller coaster of prices, roller coaster of net load in demand? And I'm sure many of you there who work on geothermal have seen this in more detail than is here, but this shows where geothermal gradients are relatively good, where we have relatively good temperature gradients. And the yellow is hydrothermal spots, but far more parts, especially of the western half plus parts of Texas, have relatively hot rock deep underground than have steamy hot springs or hydrothermal right near the surface. The bottom shows a meeting that I attended. Secretary Jennifer Granholm, Secretary of Energy, came, hosted by that's our president, Reggie DeRoche, and Jonathan Aho Franklin, a professor here, when she announced the DOE target of aiming for $45 a megawatt hour enhanced geothermal, not just the traditional hydrothermal, but enhanced geothermal, shown on the right, where you would inject and get heat from several kilometers beneath the surface. Their aim is to have 45 megawatt hour costs by 2035. Now, what would that mean for the environment? For the environment, for climate, and I'm coming at this from an atmospheric science perspective, is where my core training came before getting into the energy systems modeling. The atmosphere doesn't care whether we go with wind, solar, ocean energy, nuclear energy, geothermal. All of these are factor of 10 cleaner than traditional fossil fuel technologies. Even fossil fuel with carbon capture doesn't get 100% carbon capture, still has methane leaks on the way to the plant, still needs power to come from somewhere to run the carbon capture device. So yes, fossil fuel with carbon capture can be substantially cleaner than traditional plants, but geothermal and all the other nuclear or renewable options are far cleaner than those. So we can be splitting hairs about exactly which one's higher than others, but the point is to get away from fossil fuels to any of these options on the left. In terms of cost, where geothermal sits is that most of these costs have been what it's been for traditional geothermal facilities. Most of those that are being costed are hydrothermal, and enhanced geothermal, we're going to start seeing costs coming forward, but has been a bit higher than that, is trying to get to this cost range at first. And you see that it's a bit higher cost range than where it's very sunny and where it's very windy. These are all unsubsidized costs before you count in the tax credits that now geothermal is starting to get, on par with what wind and solar have gotten for a long time. So it's in the mix. It's certainly far more affordable than nuclear. It's hard to know what nuclear costs because we're about to open the first two reactors since I was a toddler back in the 1970s, and they've had factor of 3 cost overruns that helped to bankrupt Westinghouse in the project, but in the process. But geothermal is already probably less than half the cost of nuclear. So a lot of attractiveness in terms of a dispatchable option. It looks more expensive than wind and solar, but what I show on the right is what if you have to firm up the wind and solar? What if you have to have battery backup? What if you use natural gas to fill in the times when it's not windy and sunny? And this is analysis that's done in different parts of the country. So CAISO is California, SPP is the Southern Power Pool, PJM is a Mid-Atlantic grid. And you can see if I take those geothermal costs and look at where they fall when you have to make wind and solar less intermittent, it becomes competitive with that in various parts of the country. How can we push this even further to where it gets to the point of being more attractive? This is something that I focused a lot on in my book that came out in 2022, is the concept that the policies that we need, the technologies that we need, we can be agnostic about whether we get there with a carbon tax, with subsidies, with voluntary measures, and so forth. But we really need two things if we want geothermal to start going on the cost curves that have made solar and wind the cheapest forms of electricity. In history, we need a technology push coming from research, development, and demonstration projects showing that these technologies exist, making them work more effectively, making them available. But I draw far more people on the demand pull side, far more of the movement of getting this boulder down the hill, a hill that fortunately is rolling downhill, but has huge amounts of friction to it, and we need to move faster than ever. That's the demand pull that comes from doing it more, comes from saying, if you build this technology, we will buy it, we will deploy it. And the more that we deploy something, the more the costs come down. That can come really whatever means you want: procurement, incentives, taxing the competitors, mandates, whatever it may be. Anything that tells industry there's going to be a demand for this can lead to more deployment. And what we've seen across technologies that can be modularizable, LED lights, Model Ts back in the day, batteries, solar, wind, they've all followed cost curves that these have come down. How do we make geothermal go along similar cost curves? Where we've seen of where these technologies are, this came from IRENA a year ago, the International Renewable Energy Agency. And what they show is that across all different renewable technologies, a key thing is that can be modularizable, that can be commoditized and done again and again and again with factory produced options. They've historically followed these cost curves, sometimes called Swanson's law, where costs have declined 20% or more for every doubling of global deployment. So here, what's shown on the x-axis is the cumulative amount of these technologies that have ever been deployed globally. On the y-axis shows what do they cost in terms of dollars per kilowatt hour, adjusted to 2022 inflated dollars. And you see this amazing reductions in cost that all of the technologies have had. Concentrating solar power, we haven't seen development very much. That's where you have the mirrors. And yet it is on a pretty steep cost curve. Of course, what's become the cheapest has been wind on land in gray and solar on land in yellow, so solar photovoltaic. These have become the cheapest forms of electricity in history, in part because we're doing them so much, in part because we've been doubling global deployments nearly every year or every 2 years in recent years, and the costs have come down. Offshore wind is still expensive, and probably the cost ticked up last year when we had such high interest rates and had some supply chain bottlenecks. But offshore wind certainly has a lot of potential. If you look at what land-based wind cost when we only had this much deployment, offshore wind is actually ahead of the curve because of those strong winds, because of the very large turbines being built there. So certainly potential for that to go on similar cost curves. The star shows where geothermal is. Is it still really unproven how low can costs go? It's actually doing better for a given amount of deployment than some of these other technologies did. It's way ahead of the game compared to where wind and solar are. We just haven't been doing it much yet. So will it be possible to have geothermal go along these cost curves that by the time it's deployed more and more, it could get to be competitive or cheaper than wind and solar, and especially perhaps get at higher value because of the firm or flexible nature be deployed. Again, lithium-ion batteries look like a similar curve. Geothermal deployments are starting to grow. So can this growth outside of North America, can this growth that we start to see in the US lead to more affordable approaches? We haven't seen this yet. If you look at where the cost trends have gone, geothermal costs have been pretty flat, have actually gone up 8% on a real cost basis since 2009, over a period when solar photovoltaics have fallen by 83%, wind has fallen by 63%, nuclear has increased by 47%. So how do we get geothermal to look more like wind and solar and less like nuclear? There are scenarios where we would start to get the deployment that we need to bring down those costs. This is where NREL looked at what if Department of Energy and partners that help drive those cost curves down are able to achieve the cost reductions that are sought, which would mean an 80 to 90% cost reduction in enhanced geothermal, not hydrothermal, but enhanced geothermal, getting down to those costs, getting down to that $40 or $45 a megawatt hour range. And they think that in that case, we could get enormous amounts of geothermal deployed. Still going to be less than solar or wind, but this is a pretty substantial amount of geothermal they think could be deployed, but with two conditions. In NREL's analysis, you would both need to get costs down to the Earthshot target by 2035 and then have it continue go down after that. And a key and in here is this is with a mandate for a net zero economy. It was taking our Paris commitment seriously, saying that we're going to be net zero by 2050. They think that geothermal would be a big part of the mix of getting there. And in the blue, it shows where this would be deployed. And these are the assumptions that went into that study of business as usual costs compared to what they think the amount of cost reductions would be, much more successful drilling rate, much better flow rates, huge reductions in cost to be able to achieve that. But in their expertise, they think this is doable. So what have we modeled here at Rice, looking at similar scenarios? We deployed the Reeds model, which is a capacity expansion model for the United States that was developed by NREL and splits up the country into the 134 balancing areas shown. So it has supply and demand within each area. It has transmission modeled between the areas. It has the main interconnections of the country. And we developed our own cost assumptions. This is what will be table 2 of a paper that we'll soon submit, but please don't cite it since it's about to go through peer review next month. And so these are assumptions that we made. And in this case, we looked at what had been assumed in previous studies, and we used 3 costing models to get our estimates. We used this model called GET'em, which is built into most models such as Reeds. We also looked at cost estimates from geofires, and we used a model called Questor, which is used by the oil and gas industry because we're operating under the assumption that we started deploying some of the technologies that have made fracking cheap, technologies that have made horizontal drilling cheap, that it could bring down costs. And so we based some of our drilling cost estimates on the Questor model, blended those with the GET'em estimates. And then the question is, if these are the costs today, these are, say, 2023 costs, as we estimated, how will it trend down from there? And that's what's really crucial, is that even with these assumptions that oil and gas technologies are making things better, it still needs to trend down dramatically in cost, or we're not going to deploy this at all. And so we had assumptions, a conservative case, a moderate case, and an advanced case. And the advanced case assumes that we get more than 70% reduction in cost by the late 2030s and drifts down after that. And what it ends up is this advanced curve ends up giving you something close to equivalent, not exactly the same, but as close as we could come to mimicking if Department of Energy's Earthshot is successful in bringing costs down to around $45 a megawatt hour. We looked at supply curves. So we, under each of those cost curves, we said how much capacity is available of geothermal at each given cost point. We did a sort of supply stack of those. There's enormous amounts of potential. There's lots and lots of hot, dry rock out there. Of course, we're only going to deploy a small portion of this. But just for comparison, the ERCOT grid has about 100 gigawatts on it. We're never going to deploy nationally this many thousands of gigawatts, but it's out there if those resources were accessed. And under the advanced scenario, as I said, most of it would be too expensive to adopt, but these dots show that you would start having, under the best conditions, costs that would get down to that. The pink line shows the $45 megawatt hour target. With the advanced cost curve, you start having substantial number of spots where you could do enhanced geothermal at competitive prices. So we modeled what the capital cost would be under each of these scenarios, and we modeled what the levelized costs would be, again, under the advanced. And here we look at what would it be for the cheapest 25 gigawatts that you could deploy all the way out to the cheapest 1,000 gigawatts that you could deploy. As 1,000, you're really, really dramatically changing the entire national grid. 25 gigawatts, think of that as like the size of 25 coal plants or 25 nuclear reactors. So as you need to take more and more expensive, less and less favorable options, of course, the costs go up. But here we think that there could be a large amount, if we can hit those advanced cost curves, there would be a large amount, even up in the many hundreds of gigawatts of capacity available that could be done at costs of $50 a megawatt or less. Where are those located? The very cheapest resources are located out west, especially in Nevada and Idaho. As you start to go to larger and larger amounts of deployment, you have broader areas of the West, and even you start to see Texas show up a little bit as having geothermal potential there as well. So how would this be deployed? what we looked at was, what if we have the moderate cost reduction scenario on the left, or what if we have the advanced cost reduction scenario on the right? If we have moderate cost reduction, no matter what policy we assume, there's not going to be that much deployment. Even these are numbers for the year 2050, I should have labeled. Even if we require deep decarbonization, but we only get moderate cost reductions, it's still probably just going to be in this ballpark range, well below 100 gigawatts. Again, the Texas grid alone has more than 100 gigawatts of overall supply today. So we're not talking, if we only got up to 29 nationwide by 2050, we're not rocking the boat. Where we could really get the big numbers come in is if we get both advanced costs and a policy that requires very high amounts of decarbonization, and found that you really need to go all the way if you want to go to this. If you still allow there to be 5% of today's emissions, you'll keep a lot of natural gas plants around, only operate them perhaps 10% of the time. But because they don't operate very often, they don't give off much emissions, they're already built. And so at least an optimization model wants to deploy those to fill in the gaps. When you can't have those anymore, when you have to go 100%, and so even partial carbon capture doesn't get you there, that's where, if you have geothermal hit the Earth-shot targets, the model thinks it would become the most affordable way to fill in those gaps between wind and solar without needing to just go bonkers with the amount of batteries you build. And so it becomes a pretty sizable amount of the grid. We also looked and found, if you were to subsidize geothermal about the amount of subsidy that perhaps it's getting from things like Google that are doing the power purchasing agreements, or like some subsidies that have been available for similar technologies, you might get some substantial build out as well, even without any of the CO2 explicit policies. Where would that go? Under existing policies, the growth would be out west. If you started to get to advanced curves and you started to get to requiring 100% decarbonization, those, since this is a Texas audience, your eyes could light up. This is where you see Texas could become the epicenter of wanting to do it, being on the isolated grid, being a place where we have those 10% of the time when wind and solar can't get the job done, and where we have enough hot rock in the certain, especially eastern parts of the state. You could see, if we had to get to net zero, that this could be one of the best places to build geothermal in the country. This is how we might head towards there. A lot of the build out, if we don't require net zero until 2050, you might not start getting a lot of that deployment until the late 2030s and the 2040s. And what does this mean in terms of how geothermal would fit into the mix? Again, orange is the geothermal. If we don't have both, improvements in technology, reductions in cost, and also have policies that are favorable to geothermal, then geothermal is going to be these tiny orange slivers. If we have both, then we'll see geothermal be this substantial part of the mix, which would mean huge growth for the industry. And in that case, it would be nearly 10% of capacity. It would actually be 15% of generation. So on the left, I show what is the capacity. On the right, we take account of the fact that geothermal can operate more than 80% of the time, whereas solar and wind farms don't operate nearly as often. So it could be a pretty sizable part of our generation mix, as shown on the right. So some concluding thoughts, and I think, yeah, right on time for ending at 9:45 to leave lots of time for questions. Enhanced geothermal opens up far more potential resources, far more places we could go than hydrothermal does. The technology advances and the technology transfer that we can get from the oil and gas industry that has so much expertise in drilling deep, in drilling horizontal, in injecting fluids, those can be transferred. There are challenges with the hot temperatures, challenges with the different conditions you get in good geothermal wells, but a lot of that can drive that learning by doing what we need, that technology push that we need if there's the market pull to go with it. For now, geothermal is costlier than wind and solar, and for now, we have plenty of gas, we have plenty of coal, we have plenty of nuclear and hydro dams to back up the wind and solar. We don't yet need geothermal. So with it being costlier, we're going to need that market demand pull. We're going to need early adopters, like what Google is doing, like what's happening in California, where California has that clean, firm mandate, get those early deployments that can bring us down those cost curves. Have the technology push coming from things like DOE's Earthshot, have the demand pull that's coming from those early adopters, from those favorable state or corporate policies, get us on that curve that we would like to be on. But we're going to need that to be combined with supportive policies, whether it's a climate mandate, whether it's subsidies, whatever it may be, something is going to need to get this to budge. It probably can't get to the point, because wind and solar and batteries are getting so cheap. We can't probably do it alone just on pure economics if policy doesn't play a role as well. Some future directions we want to take this, and I really would love to find ways and hope I can come out and visit the Bureau later this year and find ways to collaborate with you. We'd like to take what we modeled in READS and compare it to another model. We're thinking that PyPass, which is a Python-based power system analysis model, an open source model, could be a good way to see if a different modeling platform is giving us similar results to READS. We want to look at how geothermal can enhance reliability in a place like ERCOT that has the constraints of being an isolated grid. READS only divides the year into a couple dozen time slices. It doesn't look at how well we're prepared for a deep freeze like next week, or a record heat wave like we had last summer. And so really want to dive deeper into some localized places, look at some extreme weather events, and see, could geothermal maybe have a bigger role than a more generalized model like READS thinks. Look at some additional environmental and economic metrics that might give value to the lower land use, the lower footprint that something like geothermal has. And what we'd really like to learn more from Ken Wizian, from others at UT or at SMU or other places, is could we do a better job if we had better subsurface data, a place where we have really good data and can go better than what we had. We were still relying on the NREL and SMU geothermal temperature gradients. We've been hearing that there could be steeper gradients, there could be more favorable conditions in some places, could be better localized information. So can we work with you? Can we work with others, work with Project Interspace to carry this forward? So I'll end there. I think we're right at 9:45 and welcome your questions.
Thank you. Thank you for the talk. Oh, we have a hand up already. Ken, please go ahead.
Okay, thanks. Hey, great talk. I really appreciate the work you're doing. Particularly, we need these new studies, because everything that's done more than about 2 years ago doesn't really take into account the geothermal anywhere mix. And yes, to reinforce what you just said, in the now 5 or 6 counties in Texas, pretty evenly distributed, that we've looked at, we've found significantly higher temperatures than SMU or NREL predict.
Mm-hmm.
My question for you is, the Department of Defense in particular has jumped into geothermal big this year. What role might them playing the early adopter of the technology while it's still expensive, can that impact these potential decline curves in any way, or is it just not going to be a factor?
Yeah, I mean, I think early deployment is crucial, getting that out there, getting that learning by doing. And yeah, with Google, with California, with I should have mentioned Department of Defense, those are who can drive it. We have almost no enhanced geothermal on the grid today, so you can get a lot of doublings with those deployments that come early on. And what gives it the potential too is that it can be modularized like wind and solar. It's not exactly factory built. It might not have that exact same being able to build hundreds of thousands of panels in a factory in China, but it could look like fracking. It could look like where you could do the same thing again and again, not be these bespoke technologies that are designed around a single hydrothermal well. But my understanding, and you probably know this more than I do, is the Department of Defense is looking to do it on or near military-owned land, where it's not being picked just because it had a geyser there or just because it was perfect conditions, but it's doing it in places that probably have similar geology, similar temperatures to something you could replicate again and again somewhere else. And so, yeah, by having a way to test it out, having a way to get that done, I think it could look more like how fracking got cheap, more look like how something that can be cookie cutter done again and again, unlike, say, an offshore well, unlike a nuclear plant that's more like an enormous 10-year construction project that it's harder to hit those learning curves. So yeah, those early adoption, I think, can really be crucial for learning curves of geo.
Thank you.
We have a question in chat by Malcolm Ross. Malcolm, if you'd like to ask it out loud, please go ahead.
Sure. Hi, Daniel. I
Hi.
teach a geothermal course here at Rice, by the way, and also at UT. Also a co-author on geofires. So I offer up the opportunity to maybe chat some about working together. I also wanted to discuss the direct use of geothermal energy rather than converting it to electricity. Have you looked at reducing the demand for electricity by replacing the electricity that you were previously using to create heat instead and cooling, but instead using the geothermal energy directly and generally locally? So this gets to the geothermal anywhere thing that Ken was talking about.
Yeah, great question. I would love to talk to you in more depth about that. We designed our next year of the Project Interspace grant to have sort of a pivot point of either going a deeper dive and more into the electricity modeling, or having something where we look more at the heat opportunities, at the direct use heat. So I think we need to decide whether to pivot, and would love to get your perspectives on how much we should be pivoting in that way. I think there are a lot of advantages to it. The temperatures that you get from geothermal are well suited for certain applications. It's not going to give you the high temperatures you need for steel production or for certain industries, but it can be very close to the temperatures that you need for some carbon capture technologies. It can be similar to temperatures that certain industry needs. It could be used for district heat. So, and you get, better energetics, better thermodynamics by just using the heat directly rather than turning it into electricity, because, with the temperatures that aren't as hot as fossil fuel combustion get, or not as hot as fission gets, geothermal electricity doesn't have the thermodynamic efficiency that other electricity can. So yeah, using it for heat could make a lot of sense. Reeds is an electricity model. PyPass is more electricity focused, but we would love to think about how could we reduce electricity demand by using some of this heat directly. I think what we're seeing in places like Texas is we're seeing more wintertime peak demand. The levels that ERCOT is predicting for next week's freeze would be getting up as high as the demand was in this record summer heat wave that we just had. So there's this need to be thinking about how do we reduce electricity demand at peak times of winter? How do we get more sources of heat? So would love to be looking at that, but no, we have not looked at that yet.
Thank you. If there are no other questions, I'm happy to raise the point of closed loops, and whether you focused on EGS, but there's also the technology fast following perhaps EGS is closed loop geothermal. That also goes to the geothermal anywhere thing, where you create loops where you need the energy, whether it's heat or electricity. What about adding that into the mix as well?
Yeah, I guess I considered that, and maybe I used clumsy shorthand, but I considered that among the enhanced technologies,
okay,
as distinguished it of hydrothermal, where you have the special hydrothermal conditions, and by enhanced I meant the closed loop, or the Ever style approach, or the Fervo style approach, or
okay. The DOE makes a distinction between EGS and closed loop, so it's important if you're going to lump them to say so.
Okay, good point.
All right, do we have any more questions? That might be it. Thank you for giving this talk to us, Dr. Cohan. It was very informative. And if anyone who's watching the recording, or anyone right now has a burning question but they're afraid to ask, please reach out to the speaker via email. And thank you for your attendance.
staying here.
Thank you. Appreciate the opportunity.